In the previous class, we have gained an insight as to how when you elevate the temperature of a gas and quickly cool it by letting it flow through a nozzle, it results in the creation of population inversion. This scheme was first conceptualized by two American scientists, Abe Hertzberg and Ian Harley. However, their attempt in 1965 to establish population inversion between the electronic energy states of xenon gas was unsuccessful. So they basically used xenon, and it has its electronic energy states. The energy levels rapidly approaches each other with increasing energy, and this is xenon. So these electronic energy states, when they elevated the temperature and quickly reduced the temperature of the hot gas, they were not successful in creating population inversion that was prerequisite for effective process of lasing. That is because they were perhaps the relaxation of energy from relaxation of molecules at different energy levels did not relax in the appropriate way that is prerequisite for effective state of population inversion. The invention of a gas dynamic laser is, however, credited to Edward Geary and Arthur Robert Kantrowitz of AFCO Everett Research Laboratory, located in Massachusetts, in the USA. They succeeded in inverting the population between energy levels of molecular vibrations and operated the first gas dynamic carbon dioxide laser. So they made use of carbon dioxide molecules, molecular gas of carbon dioxide, elevated its temperature, then subjected it to a rapid expansion by flowing it through a nozzle, and created population inversion between two corresponding energy levels of the carbon dioxide, and achieved and demonstrated the first ever operation of a gas dynamic laser in the year 1966. The operation of a carbon dioxide gas dynamic laser was subsequently realized in 1970 by Robert L. McKenzie at the Ames Research Center at NASA, California, United States of America. You see, the gas dynamic lasers are capable to generate quasi-CW power to the tune of tens of kilowatt, with potential of exceeding even 100 kilowatt. You see, quasi-CW means that although it is a CW laser, but it really does not work continuously, endlessly. It works in a continuous mode for a substantial time, maybe tens of milliseconds, hundreds of milliseconds, and then it stops. But over this substantial time, it can maintain power which is tens of kilowatt, and even can go to the extent of even 100 kilowatt, which is extremely high continuous power. This capability makes such lasers particularly suitable to serve as high-power laser weapons for military applications, because in such quasi-continuous operation, the laser can deliver huge amount of energy on the target. And can easily destroy this, damage the target quite extensively. And that is why such lasers have gained a lot of popularity to serve as high power laser weapons basically meant for military application. And with regard to industrial or civil applications, gas dynamically pumped lasers have not generated much interest, as they are unable to match the construction and operation simplicity of their electrically pumped counterpart. Because the operation of such lasers is quite complicated, complex. This elevation of temperature, then rapid cooling, and then flowing that cool gas through resonator cavity is more challenging than the operation of conventional laser, gas laser, based on conventional pumping methods like electrical pumping. And that is why they have not gained much popularity for industrial and civil applications. All right, let us now get into the details of operation of gas dynamic carbon dioxide lasers. We first consider, before moving into the gas dynamic operation, we consider the low-lying energy levels that participate in the process of lasing carbon dioxide. Low-lying energy levels of carbon dioxide molecule. As you know, that it has three modes of vibration: symmetric mode, bending mode, and asymmetric mode. The bending mode, of course, is there are two types of bending. Basically, there are four modes of vibration because it is a triatomic molecule, because 3n minus 5 equal to 9 minus 5 equal to 4. Four modes of vibration. But we are showing three modes because bending the molecule can have bending in both on the plane of this paper as well as on a direction perpendicular to the paper. So both are represented here. So basically it has four modes of vibration. Symmetric mode. In the asymmetric mode, as you can see, the quantum of energy required to excite an asymmetric mode of vibration is the highest, and which is more than the quantum of energy required to excite a symmetric mode of vibration, and of course more than the energy required to excite a bending mode of vibration. But another important point that I would like you to note here is that the fundamental energy of bending mode, that is this energy, is nearly half of the energy, fundamental energy of symmetric mode. That means that 2 quantum of excitation of the bending mode is almost same as single quantum of excitation of symmetric mode of vibration. If they just lie 0 to 0, that is second excited bending mode is almost nearly matched to the first excited energy state of symmetry. So now we consider a collection of hot carbon dioxide gas. That means you have elevated the temperature of the gas, and also you have taken it at a high pressure. Why high pressure? Because at high pressure, the number of active species also will be more. That means you will be able to generate more output power from the laser, simply because the number of light emitting species is more. So high pressure, and we also have elevated the temperature of the gas. Now at an elevated temperature, a significant fraction of the molecule will move away from the ground state to the higher vibrational states, following a Boltzmann distribution. We now know it very well. So asymmetric modes. Now we have shown here only the first excited asymmetric mode, or only the first excited symmetric mode, and only up to second excited bending mode. But there will be many more modes. This is the ladder of the symmetric mode. So this is 100, this is 200, this is 300, so this is 020, this is 030, then this will be 040, and so on. So the population will gradually, as the elevated temperature, the population will move from the ground state to these higher energy states, of course following a Boltzmann distribution. Now we consider, as I said, only the low line vibrational levels from the symmetric, bending and asymmetric modes of vibration that participate in the process of lasing. You know that you have already studied carbon dioxide laser. You know that there are two transitions possible. This is the upper laser level and these are the lower laser. This as well as this both can serve the role of lower laser level. The transition between this and this gives rise to lasing at 10.6 micron, and transition between this and this gives rise to lasing at 9.6 micron. Now the gas being at thermal equilibrium, the population at the upper laser level 001 will be lower than the population residing on any of the lower levels. We have raised the temperature, the molecules have moved from the ground energy level to the upper energy level, satisfying Boltzmann distribution. Therefore, the population of upper laser level is going to be less than the population of either of these lower laser levels. So there won't be any population version, so no lasing. Now this hot and compressed gas is made to expand through a tiny nozzle. This is the hot and compressed gas at high pressure. It now expands through this nozzle. So the gas expands. And as it cools into an evacuated chamber. This is an evacuated chamber. As the expanding gas cools, the population residing in the energy levels of each mode of vibration will now relax within itself through resonant VV energy transfer collisions. I just explained it just a while ago in the last class, that the molecules among these levels will collide, and through resonant VV energy transfer process as a result of collision, all these molecules will eventually come down and come here. Similarly, for bending mode, all the molecules excited to the thermal populations residing in the higher bending modes will collide among themselves, and through resonant VV energy transfer process, which is extremely fast, will come to this level. Similarly, the molecules which are residing at asymmetric stretch vibration ladder will also quickly relax through collision within this ladder, within this mode, and will eventually come and get stuck here. Because from this point, if they have to further relax, it has to be through VT relaxation process, vibrational to transitional energy transfer. The energy would then be transferred from vibrational, this is vibrational energy. If it has to come here, this energy has to go as kinetic energy of the colliding species. So then the energy gets transferred from one kind, that is vibrational to translational. Such processes are extremely slow. So let us take a deeper look into that. So as an example, we consider two CO2 molecules, one in third and the other in second asymmetric vibrational. So let us consider this is 0, 0, 0, then this is 0, 0, 1, first excited asymmetric mode, V asymmetric mode equal to 1, this is second 0, 0, 2, V asymmetric second, this is 0, 0, 3, V asymmetry 3. Let us assume that we have one molecule in 0, 0, 3 state, this state, one molecule, and one molecule in 0, 0, 2 state. So plus CO2 0, 0, 2. If these two molecules collides, then there is one here and one here. This molecule can come down to this state. So this comes down to this. So if it comes down to this much vibrational energy is released. It has come here. So this much energy is released. And this much energy can be absorbed by a molecule. So there are a number of molecules here. Can be absorbed by a molecule in the ground state. And this energy and this energy, they are same. This energy and this energy, they are same. So if this much energy is released, then this energy can be consumed by this molecule and it will climb up here at the expense of this energy. So what happens then? CO2 comes to 0, 0, 2. Already there is one CO2 in 0, 0, 2. So you have two CO2 in 0, 0, 2. Two CO2 molecules in 0, 0, 2. And then this energy is absorbed by a molecule here and it comes here. So that makes it one CO2 in 0, 0, 1. Now, what can happen next? Next, you see, there are two molecules in this state. So they can actually, each of them can come down to this state. So this molecule comes to this state. So this much energy is once again released. This will be absorbed by another molecule here. This molecule will come up here. So one CO2 molecule, this two CO2 molecule, then will give rise to two more. Each of this CO2 molecule, CO2 molecule in this state will give rise to two more molecule in the excited, this 0, 0, 1 state. So then you will have four molecules of carbon dioxide in 0, 0, 1 state, and already you have one molecule of carbon dioxide in 0, 0, 1 state. So you will have in total 5 CO2 molecule in 0, 0, 1 state. So you began with one molecule in the 0, 0, 3 state and one molecule in the 0, 0, 2 state. So they actually exchange vibrational energy among them, colliding with other molecules in different states, including molecule in the ground state. And finally, they relax to this state, 0, 0, 1. You have now 5 carbon dioxide molecule in 0, 0, 1 state. You started with one here and one here. Now they are actually gone. They are actually gone, and you have 5 molecules in the 0, 0, 1 state. So once you have now 5 molecules in 0, 0, 1 state. So as an example, you consider two CO2 molecule, one in third and the other in second asymmetric vibrational mode, and study their relaxation as they collide with themselves and ground state molecules. So then you have the relaxation through VV energy transfer. This eventually culminates in the 5 CO2 molecules in the first asymmetric vibrational mode. We just saw it. Clearly, all the molecules in this asymmetric stretch ladder, regardless of their level of excitation, will, as the gas cools, relax rapidly to the first asymmetric vibrational mode. So what it says is that all this, we have shown here only one asymmetric mode. So there will be many asymmetric modes which will be populated. Now all these modes regardless of where they are, they will collide among themselves and also with carbon dioxide molecule which is located at the ground state, and all of them now will come and reside here. So all the vibrational energy will eventually relax and all the molecules will come and reside here. That's what is being said. Relax rapidly to the first asymmetric vibrational mode. Now relaxation of the molecule from here to the ground state will involve transformation of vibrational energy to translational energy and is an extremely slow process that I just mentioned. So a CO2 molecule at 001's level, if it has to come here, say it collides with a CO2 molecule at the ground. And if this molecule has to come here, then this vibrational energy, this is vibrational energy, has to be transferred to translational energy, because if this molecule has to come here, this vibrational, it cannot have a vibrational energy anymore because it is coming down to the ground state. It cannot have any vibrational energy. So this vibrational energy, it has to carry as its kinetic energy, that is translational energy. So here the energy gets transferred from one form, vibrational, to translational. So translational energy, and it is an extremely slow process. PV transfer is very fast because energy doesn't change its form. It is just vibrational to vibrational energy transfer. And these are all resonant process because the energy difference from all these successive energy states are same. Now the rate of such VT relaxation process, however, decreases with increasing vibration. If more vibrational energy is involved, then the process becomes even slower. Now the catch here is that similar resonance VV relaxation will also be operative in the symmetric and bending modes. So all the symmetric modes, that is this, they will again collide among themselves and the ground state molecule, and they will all also appear here. And similarly, all the bending modes, this, all will collide among themselves and the ground state vibrational molecules of the ground state vibrational and will eventually come and reside here. However, since this 100 is lying very close to 020, therefore there can be good efficient energy exchange between this and this. So what essentially happens, CO2 molecule in 100 will collide with a CO2 molecule in the ground state and will result in this will come down to this much energy, and one CO2 in the ground state will climb up here. So this essentially means that if this molecule comes here, this much energy is released and this much energy will be absorbed by this CO2 molecule at the ground state and it will go up to this state. So this collision will result in creation of two carbon dioxide molecules in 010 state, like this. So that means the symmetric stretch mode will also eventually relax through vivid resonant transfer process to this level. So both symmetric and bending mode will eventually relax to this point. Now once the molecules are here, then from here to here, if they have to relax, it has to be again through VT relaxation process. But this VT relaxation process is going to be faster than the VT relaxation process between this and this, because the vibrational energy here, if I call it V1 and if I call it V2, then V1 is much more than V2. So this process is going to be much slower compared to this process. That means the molecules, once they come here, they will relax at a much slower rate compared to the molecules that comes here. So what it leads to? It leads to the possibility, thus the level 010 is much closer. The level 010 is much closer to the ground state than 01001. This level, this is V2, this is V1. So V1 is more than V2. So that's what it says. The level 010 is much closer to the ground state than 001. The VT relaxation from here to this will be much faster compared to that from 001 level. So VT relaxation, this VT relaxation will be slower. Is slower than VT, this VT. This will be faster. So then what does it say? If it relaxes slower than faster, that means there can be a situation of population inversion. This can result at some time during this relaxation process. During this relaxation process, it can result in creation of population inversion between this state and this state. So as the expanding gas cools, the lower laser level will depopulate much faster than the upper laser level. This is the upper laser level. This depopulates at a slower rate than the lower level. This results in establishing a population inversion. So this is not the lower laser level. Lower laser level, so if this relaxes faster, means this also will relax faster. This results in establishing a population inversion condition. Now, as you know, the construction of an optical cavity transfers to the expanding gas at an appropriate downstream location will make the CO2 gas dynamic laser operational. So the gas expands. As it cools, you have a cavity. This is the 100% reflective mirror. This is the partially transmitting mirror. And therefore, as this population inverted gas passes through this region of the cavity, there will be, of course, stimulated emission that will be seeded by spontaneous emission. It will result in amplification of light, and eventually it will result in output film coming out of this cavity, and the gas then eventually is pumped out and is once again available for continuation of the lasing process. Now, the addition of nitrogen and helium remarkably improves the performance of the laser, just as in the case of the conventional operation of the CO2 laser. What happens? You see, nitrogen also, as you heat the gas, if nitrogen is there, nitrogen also will become hot, and the nitrogen's first vibrationally excited level stays very close to the upper laser level, that is the first excited asymmetric mode of carbon dioxide molecule. Therefore, if a nitrogen at first vibrational excited level collides with the ground CO2 molecule, the nitrogen will come down to its ground state and the carbon dioxide will go up to the first asymmetric excited mode. This will further increase the population inversion. Similarly, if helium is added, then helium actually helps depopulate 010 level with very efficiently. So that will further reduce the ground lower laser level population, which will increase the population inversion even more. Thus, helium on the other hand plays the role of a quencher as it helps depopulate the lower laser level by efficiently removing the population from the 010 level through VT relaxation. This will further enhance the output power of the laser. In the same way as a conventional laser operates, the same role which nitrogen and helium plays, they will also play in the operation of a gas dynamic laser. And the gaseous mixture pumped out following the process of lasing is available for the next cycle of operation. So that ends our study on the principle of operation of gas dynamic laser. I hope you have understood the concept as to how a gas dynamic laser works, how the thermal energy stored in a gaseous mixture helps achieving population inversion and in turn the lasing.